Welcome everyone. Today we're going to talk about a critical, yet often overlooked aspect of industrial engineering, design for maintainability. My name is Santosh Raikar, and as a Maintainologist, I've seen too many projects start with a ribbon-cutting ceremony only to hand over a lifetime of pain to the maintenance teams. We will explore how to move beyond basic operations and focus on access, modularity, isolation, and lifecycle readiness from day one. Let's start with a scenario many of you might recognize. Imagine a composite new process line that just passed its capacity tests. On paper, it's a success. However, during the very first bearing replacement, the team discovers that the motor can only be withdrawn after removing a platform, a pipe spool, and cable tray. The nearest lifting point is rooms away, and the OEM procedure bears no resemblance to the actual layout. This isn't just a bad day for a technician. It's a 20-year financial penalty. When exactly should this have been caught? This matters because a strong system makes the right action easier under pressure. Most life cycle costs and risks are baked in before the plant is even commissioned. Maintainability isn't a late-stage review. It's a foundational project requirement. We need to engineer access for posture and lifting, design isolations to minimize downtime, ensure diagnostics provide clear fault info, and start the handover process at the concept phase, not at the end of construction. By the end of this session, you should be able to translate these concepts into measurable requirements. We'll learn how to engage maintenance teams at the right gates, review tasks using virtual or physical mock-ups before they become expensive to fix, and build a business case that balances capital expenditure with the long-term realities of downtime and labor. Our first step is to see the risk clearly. We need to identify the specific system conditions that transform routine maintenance tasks into significant enterprise risks. Before we can solve the problem, we need a shared language. When we talk about maintainability, we mean the ability to restore function under stated conditions. We need to define our maintenance concept early, deciding on things like line replaceable units, LRUs, for rapid replacement, and commit to maintainability demonstrations where we actually observe tasks against time and safety criteria, rather than just checking off a drawing. The true loss of poor design is always larger than the maintenance invoice. It shows up in safety exposure. Think increased work at height or confined spaces. It shows up in massive downtime because we spent 3 days just building scaffolding for a 2-hour repair. It impacts work quality when a technician can't get a torque wrench into a tight space, and ultimately, it drains life cycle costs through recurring labor and production penalties. Maintainability defects aren't single acts of negligence. They are chains of events. It starts with a missing requirement in the project scope, followed by late user input after the layout is already frozen. Then, we perform a paper review that misses human factors, leading to a weak handover where documentation lagged behind. The result? A lifetime of heroic workarounds that the plant eventually accepts as normal. We must break this chain before the steel is in the ground. There are always warning signs. Watch out for the access tax, where you have to take half the plant apart to get to one component, or the isolation tax, where an entire line stops because there's no local valve. We also see diagnosis tax for missing test points and documentation debt, where the BOMs don't match reality. These aren't just inconveniences. They are signals that your design process is failing the end user. I want you to ask these 8 questions of your current projects. Are requirements measurable? Are tasks defined before procurement? Do maintainers have actual decision rights at the gates? If you can't answer these with hard evidence rather than just good intentions, your system is not yet real. Now that we see the risks, let's look at how to build a disciplined operating model. This is about creating a framework where decisions are based on evidence and controls. To keep the system practical, we follow 5 principles. First, specify the task. Don't just say make it easy. Second, review early while changes are cheap. Third, treat the interface, like lifting points and diagnostics, as part of the equipment. Fourth, demonstrate reality through simulations. And fifth, only accept the project when the lifecycle support, the data and tools, is actually usable. We use the Maintain 6-gate model to make this visible. It moves from defining requirements and selecting architecture to engineering interfaces, demonstrating tasks, commissioning for readiness, and finally, learning from operation. Each gate is a filter that ensures the project only proceeds if it meets the necessary maintainability criteria. Gate 1 is about requirements. Here, the project sponsor must set clear availability and repair objectives. We define what the critical tasks are and what safe access looks like. The output here isn't a to-do list, it's an approved set of measurable requirements. Gate 2, the concept phase, is where we choose the architecture. Do we want modular replacement? Where the maintenance zones and transport routes? The lead engineer is accountable for ensuring the preferred maintenance concept is inherently maintainable before we get into the weeds of design. Gate 3 is the detail design. This is where we review 3D task envelopes to ensure a human can actually fit where they need to. We design in the lifting features and condition monitoring points. The goal is a maintainability design dossier that proves we've engineered the interfaces correctly. Gate 4 is the demonstration. Before the design is locked in, we use mock-ups or digital twins to walk the isolation and removal paths. We time the steps. If a task fails the demonstration due to a human factor issue, we fix the design now, not after installation. Gate 5 occurs during commissioning. This is where we prove support readiness. We validate the BOMs, receive the special tools, and ensure the technicians are trained. The commissioning manager must guarantee that we aren't just handing over a working machine, but a lifecycle ready asset. The final gate, Gate 6, is learning. After startup, the asset owner reviews early life failures and measures actual task times against our original requirements. This closes the loop, allowing us to update our standards for the next project. To make this work, we need clear decision rules. If a requirement is too vague, like easy to maintain, the rule says, rewrite it as an observable task. If a vendor bid is low but reduces access, we must perform a life cycle trade-off analysis. These rules prevent short-term convenience from turning into decades of bad policy. Our third section focuses on execution. How do we translate this high-level model into the daily workflow of the field? And who actually owns the data? Reliability often fails in the gaps between departments. We need one accountable owner, the asset owner. But we also need the project manager to integrate requirements and the maintenance representative to define the tasks. Operations and HSE validate safety, while the OEM provides the compliant design. Everyone has a role, but the ownership must be clear. Standard work is how we turn intent into repeatable execution. By following this sequence from requirement to sustainment and auditing it regularly, we ensure that the maintainability process doesn't just happen once, but becomes part of the company's DNA. Critical controls must be specific and observable. We don't just hope for the best. We use task envelope reviews in 3D, isolation matrices that map energy boundaries, and maintainability demonstrations that require real users to execute tasks before we sign off. We should only capture the minimum data required to change a decision. We need to know the critical tasks, the envelope required for access, how we isolate the energy, what resources are needed, and finally, the evidence that the design was accepted and the handover is ready. Measurement is key, but use measures that trigger action. Track leading indicators like early review closure and demonstration pass rates alongside lagging outcomes like the access to repair ratio. If your preparation time is double your actual repair time, your design is telling you something is wrong. Culture is sustained through management cadence. This ranges from shift-level reviews of immediate design exceptions to annual strategy resets. The goal is a rhythm that escalates problems without turning every small design tweak into a 4-hour meeting. Technology should reinforce our discipline, not replace it. 3D BM models and VR mockups are powerful because they let maintainers rehearse work before a single piece of metal is cut. Requirement systems and mobile commissioning tools ensure that data captured in the field actually makes it into the EM system. Finally, let's talk about application. How do we apply this method, verify it works, and then scale it across the enterprise? Returning to our case study, the pump that requires a platform removal. The team initially saw that capacity was met, so they were ready to sign off. But they ignored the withdrawal path crossing fixed services and the lack of lifting points. At this decision point, You have a choice. Accept the milestone and transfer the risk to operations, or stop and redesign now. If we apply our framework, the intervention looks like this. We require task-based restoration criteria. We compare isolation concepts. We redesign the layout for lifting. We demonstrate the motor removal in 3D with the guys who will actually do the work. And we hold the handover until the data is 100% complete. Success is visible when the motor withdrawal no longer requires removing unrelated pipes. It's visible when isolation only stops one train, not the whole plant. When technicians can actually reach their torque wrenches where they need to be, and the BOMs match the as-built asset, you know you've won. The lesson? Maintenance is a design user. To practice this, consider a tabletop exercise. A vendor offers a package that saves capital but requires a full shutdown for a simple seal change. Which lifecycle tasks would you model? What alternatives would you request? This is where you practice making the trade-offs before the stakes are real. Avoid common traps. Don't invite maintenance after the layout is frozen. Don't use MTTR without defining the boundaries of the task. And never close a project at mechanical completion. It's only complete when it's life cycle ready. If you see a workaround during early operation, treat it as a design defect, not a new normal. Here is a 90-day roadmap. Start small with one active project. In the first 30 days, define your critical tasks. In the next 30, run your first 3D reviews and add handover clauses to contracts. In the final month, demonstrate those tasks and adopt the standard. Create the evidence first, then scale. When talking to management, build a credible business case. Yes, there's a modest early investment in design review and mock-ups, but compare that to the recurring value. Reduced downtime, lower scaffolding costs, higher work quality, and reduced obsolescence risk. Lifecycle value is what happens when you avoid the tax of poor design. To verify your progress, use this 12-point field audit. Only score what you can actually observe or trace. If you can't show the engineered lifting path or the verified as-built drawings, then the requirement isn't met. This is about hard evidence, not intentions. As we wrap up, remember this. The cheapest time to remove a maintenance hazard is before it becomes steel and concrete. Specify by task, engage users at the concept stage, and make lifecycle readiness a non-negotiable handover criteria. Commit to the rule. No design freeze without a task review. For those who want to dive deeper, I provided a list of resources, including NASA's excellent standards on maintainability and the HSE guides on human factors. These are clickable in the digital version of this deck. I'd also like to credit the open license photography used throughout this presentation, which helps visualize the industrial reality we face every day. I'll leave you with one final question. What lifetime of pain is your next project designing today? It's time to move the maintenance conversation upstream, where options are still inexpensive. Thank you.